We'll begin with the impact of microgravity on spatial orientation and heat transfer. Then we'll use what we've learned and look at the fluid management, gas management, and fire propagation and safety. We'll then discuss how microgravity influences structural design, which will require us to also look into material selection. Finally, we'll wrap up with the human factor. Welcome to the Omar Alayli podcast, your guide to the exciting world of aerospace engineering and designing in space. I'm your host, Omar Alayli, founder of Future Space Architecture. This podcast aims to demystify and make aerospace engineering and space architecture accessible to everyone. So today, we're diving deep into the fascinating realm of microgravity environments. This podcast is for everybody, from aspiring aerospace engineers or professionals transitioning to the space sector, to high school students, educators, and space enthusiasts. Imagine a day in your life without gravity. How would that change your daily routine? How would it change how you interact with your surroundings? That's precisely what we're exploring today. Microgravity environments present unique challenges and opportunities when designing space structures like the International Space Station or space vehicles like the Orion module. By the end of this episode, you'll have a deeper understanding of how microgravity influences design choices, from simple tasks like pouring a cup of coffee in space to complex issues like ensuring the structural integrity of orbital installations. Okay, let's get started. So what is microgravity? Well, microgravity is often used to describe an environment where gravitational forces are significantly reduced. This state is also known as weightlessness or zero gravity. It's important to note that while gravity is not entirely absent in this environment, its effects are drastically diminished. In a microgravity environment, objects appear to float, and the sensation of weightlessness vanishes. This phenomenon occurs because structures and their occupants are in a constant state of free fall, while also being in orbital path, effectively cancelling out the perception of gravity. For example, astronauts on the International Space Station experience microgravity. This happens because they're in a constant free fall while orbiting around our Earth. Even though Earth gravity still affects the International Space Station, the sensation of gravity is almost completely gone. However, microgravity isn't just about astronauts floating around and having a good time. It dramatically changes the way we approach design and space construction. When we're talking about building spacecrafts, space modules, or even entire habitats, we have to throw away many of our Earth-based rulebooks and reevaluate traditional Earth concepts and adapt them for microgravity. And that's what we're doing today. So let's get into it. We'll begin with the impact of microgravity on spatial orientation and heat transfer. Then we'll use what we've learned and look at the fluid management, gas management, and fire propagation and safety. We'll then discuss how microgravity influences structural design, which will require us to also look into material selection. And finally, we'll wrap up with the human factor. So, how do you think microgravity affects an astronaut's sense of spatial orientation? On Earth, buildings have a clear down defined by gravity. The floors are aligned perpendicular to the force of gravity, and this affects everything, from how buildings are structurally designed to how we navigate them. In microgravity, there's no intuitive up and down, which means we have to consider all three dimensions when designing living and working spaces. This lack of natural up or down complicates how we plan and arrange interior spaces. So how do we solve this? Well, first, a spaceship or station ends up having its own relative coordinate system. For example, in low Earth orbit or LEO, the standard orientation nadir considers Earth below you as down, and the up vector opposite to nadir is zenith. Another way is by utilizing multi-directional designs for the structures. Those designs are aided by visual and tactile cues, which can help astronauts adapt and get oriented. Those cues are usually placed around the hatches that connect the modules. Think overhead and deck for up and down, starboard and port for right and left, and forward and aft for front and back. Also, handrails and foot restraints and Velcro straps are used to facilitate movement and provide an illusion of orientation. On the International Space Station, in addition to the overhead and deck signs, lighting placement is used. You will notice that the lights in the modules on board the International Space Station are always on the overhead or ceiling, and the light was always pointing down to the deck, which stimulates what we are using here in our daily lives here on Earth. Next, let's talk about the concept of heat transfer and how it's influenced by microgravity. On Earth, we're used to 3 types of heat transfer principles: conduction, convection, and radiation. Each of those 3 heat transfer principles behave differently in microgravity, and today we're going to unpack why that matters. First up, conduction. This is the transfer of heat through a solid material without the movement of the material itself. Think of a metal spoon in a hot cup of coffee. The heat travels up the spoon to our hands. In microgravity, conduction takes on a new level of importance, especially for thermal control and management. Why? Because convection is mainly absent. So what is convection? On Earth, hot air rises and cold air sinks, right? That's how we get wind and natural currents. But in microgravity, this natural circulation doesn't happen. Heat doesn't rise, it just kind of stays. This has massive implications for heating, ventilation, and air conditioning systems. Remember, we're talking about off-world structures where we expect humans to live and work. Without natural convection, we can end up with pockets of hot or cold air. This can cause discomfort, risk to the crew, and even affect equipment. That is why engineers have to use fans and other mechanical methods to circulate the breathable atmosphere and maintain a comfortable and a safe environment. In a closed spacecraft or space module environment, poor air circulation could lead to dangerous situations like the buildup of carbon dioxide pockets. The third heat transfer principle is radiation. This is the transfer of heat in the form of electromagnetic waves, like the heat from the sun reaching Earth. You see, in microgravity, radiation becomes the most reliable method for heat transfer in thermal management systems. This requires careful use of material selection and design strategies. For example, spacecrafts often use reflective material to minimize heat absorption and use radiative cooling systems to dissipate excess heat into the vacuum of space. An example of that is the photovoltaic radiators on the International Space Station. These radiators are designed to dissipate excess heat generated by the International Space Station systems and its crew into the vacuum space. Those radiators are coated with materials that have high emissivity, meaning they are very effective in emitting thermal radiation. The third concept influenced by microgravity we're discussing today is fluid management. Because of lack of gravity, liquids do not flow naturally down or settle as they do on Earth. So designing systems to manage fluids becomes crucial. Surface tension becomes dominant, causing fluids to cling to surfaces and form spherical shapes. Also, with the absence of buoyancy-driven convection, heaters and coolers must be designed differently, as hot fluids will not naturally rise and cold fluids will not sink. Pumps and cooling loop systems must be used inside and outside the craft or space station. In microgravity, there's also issues with fluid stability and sloshing. Without gravity, fluids do not settle, complicating the design of fluid storage and transfer systems. This could even impact dynamic load calculations. So fluid management in microgravity environments has significant implications on everything from drinking water to fuel storage. Consequently, in designing a pressurized space that the crew and astronauts need to use, whether to eat, hydrate, take a shower, and use the toilet, understanding fluid dynamics and how to mitigate its challenges becomes front and center in our designs. This, of course, extends to thermal control, plumbing, water recycling, and hygiene systems, which are essential components for maintaining a healthy living environment in space. Gas management is another area that gets complicated in microgravity. On Earth, gases, just like fluids, mix easily due to convection. You know, the same principle that makes hot air balloons rise. In space, gases can stratify and stagnate. Imagine a pocket of oxygen in one area of a module and another pocket of carbon dioxide in another. This variation in gas composition in confined spaces is dangerous. You see, the pocket of oxygen could pose a fire risk, while the pocket of carbon dioxide could be hazardous to astronauts and crew. High levels of CO2 can lead to headaches, increased heart rate, muscle twitches, confusion, and in extreme cases, organ damage. So how do we manage those risks? We manage them through subsystems like the air revitalization subsystem used in the International Space Station. The air revitalization subsystem uses fans, chemical scrubbers, or sorbent beds to maintain a consistent and breathable atmosphere. Sensors are also used to monitor gas concentrations continuously, alerting astronauts if levels go out of the safe range. But the challenges don't stop there. Future long-duration missions may require more advanced gas management systems that can handle not just the spacecraft's internal environment, but also interacts with the external environments like the Martian atmosphere. Okay, so far we have discussed the influence of microgravity on 4 traditional systems we take for granted here on Earth: orientation, heat transfer, fluid dynamics, and gas management. Now, let's talk about something that's both fascinating and a bit scary: fire in microgravity. You might remember from your school days that hot air rises and cold air sinks. Think floating lanterns when we used to make them out of our paper bags, lunch paper bags. But in microgravity, the rules change. Fire behaves quite differently, spreading spherically in all directions instead of rising upwards. Imagine a floating ball of fire. Sounds something like a sci-fi movie, right? Well, in microgravity, there's no buoyancy-driven convection. That's a fancy way of saying that hot air doesn't rise and cold air doesn't sink. This has a profound impact on how flames propagate, causing them to become spherical and spread in ways that are counterintuitive. So why should we care? Well, fire in a closed environment, like a spacecraft, is a significant safety concern. It's not just about the flames. It's also about the smoke and toxic gases that can be produced. These can quickly fill the confined space, risking both our astronauts and the equipment. One of the first lines of defense is using fire-resistant material in the construction of spacecraft and space habitats. These materials are designed to withstand high temperatures and prevent the spread of flames. Orthofabric is one example. It's a blend of Gore-Tex, Kevlar, and Nomex fiber. Some use of orthofabric is as the outer layer of the astronauts' spacesuits. Another line of defense against fire is early detection, but traditional smoke detectors may not work effectively in microgravity. That's why researchers are developing state-of-the-art detectors that can identify smoke particles in unique conditions of a spacecraft. These detectors use advanced sensors, near-infrared forward light scattering laser devices, and algorithms to provide early warnings, giving astronauts more time to respond. But what if a fire does break out? That's where fire suppression systems come into play. It's more like a 3-step process. First, turn off all the fans. No air circulation means no feeding the fire with more oxygen. Step 2, disconnect electricity from the units or racks that the fire is propagating from. And third, after the astronauts wear protective clothing, they use fire extinguishers. These aren't your average fire extinguishers. They're explicitly designed for microgravity environments and use carbon dioxide to suppress flames. So next time you see a video of astronauts playing with fire on the International Space Station, and yes, they do conduct controlled fire experiments in space, remember that behind the mesmerizing spherical flame is a world of complex science and engineering designed to keep our space explorers safe. All right, the 6th concept that is challenged by microgravity is structural design. We're talking about the structural design of spacecrafts, space stations, and habitats. When we think of structures on Earth, bridges, buildings, or dams, we think of them as things that need to stand up against gravity. They need to be strong enough to support their own weight and the weight of the people and things inside them. Weight being mass times gravity. But in space, that equation changes dramatically. Actually, in microgravity environments, structures don't have to support their own weight because there is no gravity. Sounds easy, right? Well, not so fast. They do have to withstand forces from other sources like tension, compression, acceleration, and external impact. The International Space Station has to deal with those forces all of the time. As an example, it's in constant freefall and influenced by atmospheric drag. Not substantial atmosphere, but enough forces to require it to need reboosting and attitude control several times a year. So, the structure we are designing has to be robust enough to handle those dynamic forces without experiencing structural failures. To this point, some types of structural failures that can occur due to dynamic forces are buckling, fatigue failure, resonance, or shear failure. Let's break these down before moving on. So buckling mostly happens as a result of compression due to forces applied on a slim structural element causing them to bend or fail. Support beams or struts on a spacecraft are rigorously designed to prevent them from buckling under dynamic forces from sudden maneuvers or impacts. However, fatigue failure happens when we apply dynamic forces on a structure repeatedly, which could cause the material to weaken over time and eventually break. As for resonance, every structure has its natural frequencies at which it vibrates. If a dynamic force causes the structure to vibrate at matching frequencies, it could cause resonance, leading to catastrophic failure. If you ever lived near a highway like I did, you might have experienced your living room glass window vibrating suddenly when a cargo truck passes by. That's resonance. As for shear failure, it happens when a structural element, like a beam, that is designed to absorb loads in one direction, is exposed to dynamic forces from a different direction, which causes layers in the material within the structure to slip or slide past each other. Early signs of shear failure is seeing cracks at the tension side of a beam. Okay, we have just discussed dynamic loads implications on structural design. Another critical loads we need to address are the forces applied during the rocket launch phases. The forces experienced during a rocket launch are immense. Absurd. We're talking about 7.6 million Newton or 1.7 million pounds of thrust at sea level. That's for Falcon 9, and reaching speeds that exceed 6,700 kilometers per hour at the main engine cutoff for the second stage separation of a rocket. And that's around an altitude of 80 kilometers above sea level. The structural design has to account for those absurd forces to ensure the integrity of the spacecraft or module during the delivery and deployment phases. This brings us to the concept of load distribution. On Earth, architects and engineers worry about how to distribute loads to counteract gravity. In space, the load distribution is more about dealing with the internal pressure and the dynamic forces. These structures must be designed to distribute those forces evenly to prevent any weak points that could compromise the integrity of the spacecraft or habitat. Now let's talk about pressure. In a spacecraft, a space module, or a moon habitat, the walls may need to be strong enough to withstand pressure difference between the inside and the vacuum of space. This is a different kind of load that doesn't exist on structures here on Earth, except underwater structures. It's not about supporting the weight of the roof in the traditional sense. It's about keeping the inside in and the outside out, so to speak. So as you can see, structural design in microgravity is a whole new ballgame. It challenges our Earth-centric notions of architecture and engineering, requiring us to rethink how we design for strength, stability, and safety. It's a topic that combines physics, engineering, and a touch of imagination to solve problems most of us have never even considered. But for those aiming to make humanity a multiplanetary species, it's all in a day's work. Okay. With that out of the way, another concept challenged by microgravity is material selection. You might think, hey, just pick the strongest, lightest material, right? Well, not so fast. Picking the right material for space structures is a nuanced task that goes beyond just strength and weight. It's about knowing what each part of your space structure needs, whether it's a module, a spacecraft, or a living space. So let's break it down by function and location. When we're talking about function and location, we're talking about what each part of the structure is supposed to do and where it's located. Is it an external wall that needs to protect against micrometeoroids? Is it an internal structure that needs to support equipment? Or is it part of a life support system that needs to be both strong and chemically inert? All right, Let's dive into material selection for space structures, starting with the exterior walls. Imagine this: your material needs to be a superhero, strong enough for to face the vacuum of space, whether potential impacts from space debris and or other extreme temperature fluctuations, and withstand statics and dynamic loads and forces like tension, compression, torsion, and bending. Take SpaceX's Starship, for instance. They've gone for stainless steel T304L for the body, and they're using their own SX500 superalloy for the critical parts of the Raptor engine, like the turbopumps. As for Starship's hexagonal heat shield tiles, they're making them out of aluminum, lithium, and carbon fiber. Why? Because materials like stainless steel and aluminum alloy are like the Swiss Army knife of space. They're strong, lightweight, and can handle thermal extremes. But wait, there's more. Ever heard of Whipple shields? These are like the body armor of space vehicles and modules, designed to take a hit from flying debris and micrometeoroids. The first line of defense is the Whipple shield's forward bumper, and it's got one job: to change the state of any incoming projectile. A fancy way of saying breaking them down into smaller pieces while changing their speed and direction so that the next layer can absorb the impacts. Think how our atmosphere breaks down a meteor as it falls down to Earth. Traditionally, aluminum alloy have been the go-to for those front bumpers. Lightweight, yet strong. But innovation hasn't stopped there. We're seeing hypervelocity multi-shock impact shields made from ceramics, metallic foam panels, honeycomb panels, and even super composite mixtures. The result? Impact shields that are more durable, safer, and perform better than ever, which is what we need for long-term missions outside the orbit of our Earth. Now, what about internal structures? Those don't have to deal with the vacuum of space, but they do need to support equipment and withstand forces generating during maneuvers. Lightweight materials like titanium and aluminum alloys are often used for those purposes. They offer excellent strength to weight ratio and are relatively easy to work with. Moving on to life support systems. These need materials that are not just strong, but also chemically inert. You don't want your life support systems corroding or reacting with other materials or substances. For example, the oxygen and nitrogen tanks are made of steel with graphite composite overwrap, while their supply lines are made of Monel alloy, mainly nickel 50 to 60% with some copper and other elements. On the other hand, the tank's distribution lines are made of stainless steel. So, as you can see, material selection in microgravity is far from one-size-fits-all solution. It's a complex, multifaceted challenge that requires deep understanding of material science, engineering, and specific needs of each part of the structure. It's another example of how microgravity forces us to rethink even the most basic concepts and come up with innovative solutions. Last but not least is the human factor. Now, you might be thinking, what's so complicated about humans in space? We fly, we float. Well, let me tell you, it's a whole Pandora's box of challenges which the field of human factors have to address. So what's on the radar for aerospace engineers and space architects? When we're designing a crewed or habitable space structure, quality of life while living and working in space is paramount. Why? Well, space is being commercialized. Missions are expected to get longer, and we are sending civilians into space with a fraction of the preparation, education, and selection criteria of career astronauts. That's not a bad thing, on the contrary, but we'd better make sure that the environment and equipment the crew, astronauts, visitors, and tourists are using are intuitive, user-friendly, and promote health and safety. So, we zoom in on 5 key areas that microgravity affects us humans biologically and mentally: neurovestibular functions, vision, motor control, cognition, and behavioral health. Yep, space travel isn't just rocket science, it's also brain science, eye science, muscle science, you get the idea. And trust me, it's a topic so rich that we'll be dedicating an entire episode to it. But for now, let's hit the highlights. First off, let's talk about the body. Microgravity is like this mischievous force that messes with your fluids, muscles, and bones. It causes fluid redistribution, muscle atrophy, which means your muscles waste away, and causes bone loss. Not fun. Now let's get into the design aspect. Space is tight. so every inch counts. When we're designing spacecraft and space stations, there should be enough room for the crew to move around and perform their duties, including emergency procedures without obstruction. The layout should also be intuitive, consistent of aid navigation, and reduces cognitive load. We're talking about designing the interior so intuitive you can navigate them in your sleep. Why? Because in space, efficiency isn't just nice to have. It's a must-have. Now, because astronauts are continuously floating around, we've got to have handrails and footholds strategically placed for movement and support. Plus, let's not forget about the exercise equipment designed to counteract the adverse effects of living in weightless environments. But what about human-machine interface? That's another area where collaboration between humans and machine is becoming ever more crucial. Let's spotlight two groundbreaking innovations: Simon, the floating AI assistant, and touchscreen controls. Simon, short for Crew Interactive Mobile Companion, is an 11-pound, 5-kilogram spherical robot designed to float and communicate with astronauts aboard the International Space Station. It's a collaboration project between the German Space Agency, DLR, Airbus, and IBM. Thanks to facial recognition software, Simon knows exactly who it's interacting with. It has a minimalist design with a wide screen that displays a face capable of making facial expressions. The best part, Simon 2, which launched to the International Space Station in 2019, can independently navigate the European Columbus Research Module, proving to be an invaluable asset to our astronauts. A floating winking Google Home. Another example of innovation and advancement in human-machine interface is SpaceX's Crew Dragon touchscreen controls. Gone are the days of clunky buttons and switches. The Crew Dragon boasts state-of-the-art touch screen controls, streamlining operations and offering astronauts an intuitive interface. It's a testimony to how technology is revolutionizing our interactions with machines. One day, not very far, the Tesla Optimus will graduate from surpassing human performance on Earth and will be trained for microgravity environments, and then we'll be living the golden age of space exploration. Until then, from floating AI companions to futuristic touch controls, the synergy between humans and machines is keeping us designers at our toes, in a good way. It's exciting for me because we're reshaping the future of designing for space. So there you have it, a quick but jam-packed overview of the human factor in microgravity. Trust me, we're just scratching the surface here. Stay tuned for a deep dive episode where we'll unpack all the complexities of keeping humans happy, healthy, and sane in our structures and ships in space. And that brings us to the end of today's episode. I hope you now have a deeper understanding of the unique challenges and opportunities that microgravity presents for aerospace engineers and space architects. I also hope you get encouraged to join our growing professional community and feel empowered to contribute to the development of space exploration. If you enjoyed this episode, I'd love for you to subscribe to this channel and share it with friends. You'll be supporting this podcast at no cost. I would encourage you to also leave a comment. I read them all. We are not sponsored, so if you can, consider supporting this podcast financially on Patreon. This will help cover the podcast expenses. Link is in the description. Also, your support helps us reach more people and build a community passionate about the future of humanity in space. Until next time, this is Omar Alayli, signing off.